The wind cut through eastern Wyoming territory, different in the winter of 1872. John McCabe learned that his first February, when ice formed on the inside walls of his cabin and his floor dropped to 18 degrees Fahrenheit, despite feeding his cast iron stove all evening. He had built and heated his cabin exactly the way every homesteader in the territory was told to do it. Tight log walls, standard stove placement, burn wood nightly, trusted and proven. By late winter, he had burned through more firewood than any man should need, yet the cold still cut through the structure. Across the upland plains, settlers were fighting the same losing battle, burning cord after cord and still waking to frozen water buckets. McCabe quietly began combining techniques borrowed from older traditions, digging deep beneath his cabin floor and filling the space with tons of river rock. Neighbors called it a ridiculous waste of effort. But when the worst freeze in decades hit that February, McCabe's cabin stayed warm for 9 straight nights without a single fire while his neighbors burned desperately and still froze. In this video, I'll break down the exact steps and principles behind his underground heat storage system. What did McCabe understand about storing and releasing heat that every other settler missed? John McCabe had not come to the Wyoming territory unprepared. At 35 years old, he carried the practical knowledge of a man who had spent 7 years on Union Pacific Railroad bridge crews, where winter construction meant understanding how steel contracted in cold and how poorly placed heating systems wasted fuel while crews still froze. His father, Duncan McCabe, had emigrated from the Scottish Highlands in 1848, bringing with him memories of crofter cottages, where thick stone hearths held warmth long after peat fires died. Most recently, McCabe had spent the summer of 1871 working alongside Crow Nation woodworkers in the Yellowstone region, helping repair lodges damaged by late spring floods. What the Crow craftsmen showed him challenged everything he thought he knew about frontier heating. While settler cabins relied on constant fire to stay warm, the winter lodges used carefully heated stone beds beneath sleeping areas. The stones were charged with long fires, then sealed beneath earth and hide coverings. Even when the central fire reduced to glowing coals, the lodge floors remained warm enough to sleep on comfortably. Yellow Wolf, the elder who directed the repair work, explained that his people had survived mountain winters for generations by storing heat in stone and earth rather than burning continuously. The concept seemed almost absurd to McCabe at the time, but he filed it away with other observations that contradicted accepted frontier practice. The standard heating wisdom that McCabe initially followed was not mere tradition, but official doctrine. The cast iron stove manufacturers who shipped products west included detailed manuals emphasizing nightly fires as essential survival practice. Montgomery Ward catalogs warned that intermittent heating led to frozen pipes, cracked foundations, and deadly overnight temperature drops. County Land Office supervisors, including the territorial foreman James Hawkins, inspected homestead claims partly by observing proper heating installations. A cabin without a central stove and adequate wood supply was considered a poorly planned claim, likely to fail and require territorial assistance. McCabe's early heating failures followed this prescribed method precisely. His cabin measured 16 feet by 24 feet with 8-foot ceilings, constructed from lodgepole pine logs averaging 10 inches in diameter. The cast iron stove sat on a stone platform near the center of the main room, with a brick chimney extending through the shake roof. He burned split pine and cottonwood, approximately 1/3 of a cord per week, following the manual recommendations for square footage and outdoor temperature ranges. Yet the system failed consistently. During December cold snaps, the cabin floor remained so cold that water spilled near the walls froze within an hour. The stove drew strongly, but much of the heat escaped up the chimney flue, which glowed red hot, while the far corners of the cabin barely reached above freezing. McCabe measured floor temperatures with a metal probe and found variations from 60 degrees Fahrenheit near the stove to 20 degrees along the outer walls. The log walls themselves conducted cold inward, despite careful chinking with moss and clay. The breaking point came during a week-long stretch when outdoor temperatures held below -15 degrees Fahrenheit. McCabe maintained his stove fire from evening until past midnight each night, burning nearly half a cord in 5 days. On the third morning, he discovered that his water bucket had frozen solid just 3 feet from the stove base. The stove had consumed wood at nearly double the recommended rate, yet the cabin interior dropped to dangerous temperatures every night. Neighbors experienced identical problems but responded by burning more wood and accepting the failures as inevitable hardships. The homestead of Marcus Stern, located half a mile east, burned through 4 full cords during January alone and still recorded indoor temperatures dropping below 30 degrees on multiple nights. Sarah and Thomas Brennan, whose cabin sat 2 miles south, abandoned their claim temporarily during February, moving into the territorial town of Douglas until spring because their heating costs had become financially ruinous. McCabe began questioning the fundamental assumptions behind stove-based heating. The railroad crews had taught him that effective heating systems required 3 elements: adequate heat generation, proper heat distribution, and minimal heat loss. Frontier cabins addressed only the first element while ignoring distribution and loss prevention. The Scottish cottage designs his father described used stone floors and thick walls to distribute and retain heat. The Crow winter lodges emphasized heat storage over continuous generation. The mockery from neighbors began when McCabe started discussing alternative approaches. At the monthly territorial supply meeting in Douglas, he mentioned the possibility of underground stone storage systems. James Hawkins dismissed the idea as unnecessary complexity when wood is abundant and stoves are proven. Marcus Stern called it Indian nonsense, unsuitable for proper homesteading. The local wood supplier, Benjamin Carson, warned that experimental heating systems voided territorial assistance guarantees for failed claims. Despite the social pressure, McCabe began experimenting during late January. He excavated a shallow pit measuring 4 feet by 4 feet and 18 inches deep beneath a section of his cabin floor. The work required removing floorboards and digging through frozen earth with pick and shovel, back-breaking labor in sub-zero conditions. He filled the pit with river stones collected during autumn, approximately 800 pounds of granite and sandstone, ranging from fist-sized to football-sized pieces. The initial test disappointed him. He built fires above the stone pit for 3 consecutive evenings, hoping to charge the stones with stored heat. While the rocks became warm to the touch, they provided little noticeable heating benefit. The stones heated slowly and cooled quickly, offering perhaps 2 hours of barely perceptible warmth. McCabe realized that his small-scale experiment had proven nothing, except that random stone placement and inadequate fire exposure would not work. But the failure taught him crucial lessons about heat storage principles. The stone mass was too small to hold significant thermal energy. The fire placement was too far above the stones to transfer heat effectively. Most importantly, the cabin envelope leaked heat so rapidly that any stored warmth escaped before it could be utilized. McCabe understood that a successful system would require larger-scale stone storage, more efficient heat transfer methods, and substantial improvements to cabin insulation and air sealing. The central challenge had become clear. Conventional wisdom demanded nightly fires because it assumed that heat storage was impossible and heat retention was inadequate. Traditional knowledge from both Scottish and indigenous sources suggested that proper thermal mass could store enough heat to maintain comfort for extended periods without continuous burning. McCabe would need to prove which approach actually worked in the harsh reality of Wyoming territorial winters. McCabe's failed pit experiment had revealed the mathematical reality behind thermal mass heating. 800 pounds of stone in 18 cubic feet of space could not store sufficient heat energy to warm 900 cubic feet of cabin air for more than a few hours. The relationship between stone mass, temperature differential, and heat capacity demanded a much larger storage system. His railroad experience with heating locomotive roundhouses had taught him that thermal systems required proper scaling to match the heat load, but he needed expert guidance to calculate the correct proportions for residential heating. That guidance arrived in February when Angus Campbell, a Scottish stonemason traveling the Union Pacific line toward California, stopped in Douglas for supplies and heard McCabe's story at the Territorial Supply Depot. Campbell had spent 20 years building stone floors and hearth systems in Highland crofter cottages, where families survived brutal winters with limited peat fuel by storing heat in massive stone foundations. When McCabe described his small pit failure, Campbell immediately identified the fundamental errors. Campbell explained that effective thermal mass required three critical ratios. First, the stone mass needed to equal approximately 10 pounds of stone per cubic foot of heated space. McCabe's cabin contained 900 cubic feet, requiring roughly 9,000 pounds of stone. Second, the storage chamber depth needed to match its width to prevent heat stratification and ensure even charging throughout the mass. Third, the fire contact area with the stones needed to be maximized through proper hearth placement within the storage chamber rather than above it. The construction work began in early March as the ground started to thaw. McCabe excavated the full 8-foot by 8-foot chamber, digging 6 feet down through clay hardpan and underlying sandstone. The excavation alone required 3 weeks of dawn to dusk labor, removing over 300 cubic feet of earth with hand tools. McCabe constructed wooden forms to shore up the walls and prevent cave-ins during the digging process. Campbell supervised the stone selection and placement techniques. They collected river stones from the North Platte, choosing granite and sandstone pieces ranging from 20 pounds to 60 pounds each. Campbell insisted on angular rather than rounded stones to create air gaps that would allow heat circulation while maintaining structural stability. The stones were sorted by size, with the largest pieces forming the bottom layer and progressively smaller stones toward the top, creating a stable foundation that would not shift under thermal expansion. The most critical innovation was Campbell's clay-lined hearth system, built directly within the stone mass. Rather than placing fire above the stones, Campbell designed a central firebox measuring 3 feet by 4 feet, lined with fire clay mixed with sand and straw. This hearth sat 18 inches below the cabin floor level, surrounded on all sides by the stone mass. The clay lining prevented direct flame contact that would crack the stones while maximizing heat transfer through controlled thermal conduction. Campbell also engineered a convection control system using adjustable vent flaps. 2 wooden flaps, each measuring 18 inches square, were installed at opposite ends of the chamber just below floor level. During the charging phase, both flaps remained open to allow air circulation that would carry heat throughout the stone mass. Once charging was complete, the flaps could be closed to trap heated air within the chamber while preventing cold air infiltration from below. The technical challenge of heat distribution within such a large stone mass required understanding thermal conductivity principles that Campbell had learned through decades of practical experience. Stone conducted heat slowly, meaning that surface heating alone would leave the interior mass cold and unused. Campbell's solution involved creating heat channels throughout the mass by leaving strategic gaps between stone layers. These channels allowed heated air to penetrate deep into the pile, ensuring that even stones 4 feet from the firebox would eventually reach working temperature. McCabe modified Campbell's basic design by incorporating drainage techniques learned from railroad bridge foundations. He installed a 4-inch layer of coarse gravel beneath the stone mass to prevent groundwater from wicking up and cooling the system. Additionally, he lined the chamber walls with split logs chinked with clay to provide insulation between the heated stones and the surrounding earth, preventing heat loss into the ground. The completed thermal mass system contained 4.5 tons of stone and 384 cubic feet of storage space. The central clay hearth could accommodate fires built with split wood up to 30 inches long. The vent flap system allowed precise control over air circulation patterns within the chamber. Most importantly, the stone mass now had sufficient thermal capacity to store meaningful amounts of heat energy over extended periods. Campbell calculated that the system could theoretically store enough heat energy to warm McCabe's cabin for 7 to 10 days without additional fire input, assuming proper charging technique and minimal heat loss through the cabin envelope. However, Campbell warned that the storage capacity would be meaningless unless McCabe also addressed the massive heat losses that plague typical frontier cabin construction. The stonemason identified specific heat leak points that standard frontier building practices ignored. Floorboards sat directly on log sills without insulation, creating thermal bridges that conducted heat downward into the ground. Gaps between floorboards allowed heated air to escape into the crawl space below the cabin. Door and window frames leaked air continuously, forcing the heating system to work against constant infiltration of cold outdoor air. Campbell's Highland Cottage experience provided solutions for each heat loss mechanism. Proper floor insulation required creating an air barrier between the heated stones and the cabin interior, while preventing heat conduction through structural members. Air sealing demanded attention to dozens of small gaps that individually seemed insignificant but collectively destroyed heating efficiency. The thermal mass chamber was complete, but McCabe now understood that it represented only one component of an integrated heating system. Without addressing envelope air leaks and insulation failures, even the properly sized stone mass would drain its stored heat into the Wyoming winter before providing meaningful cabin warmth. Campbell's Scottish cottage tradition offered the technical knowledge needed to solve these remaining challenges, but the implementation would require McCabe to essentially rebuild major portions of his cabin, using methods that territorial building practices had never considered necessary. Campbell's departure for California left McCabe facing the envelope sealing challenge alone, but the stonemason had provided detailed sketches of Highland cottage air barrier techniques before boarding the westbound train. McCabe studied these drawings while conducting his own systematic analysis of heat loss points throughout his cabin. Using a candle flame test borrowed from railroad roundhouse leak detection, he identified infiltration points by observing where the flame flickered or bent toward wall surfaces on calm days. The candle test revealed infiltration patterns that surprised McCabe with their extent and severity. The flame bent dramatically near the junction where floorboards met the log sill plates, indicating major air leakage through gaps he had never noticed. At the base of interior walls, cold air streams were strong enough to extinguish the candle completely. Most alarming, the flame danced wildly near his carefully constructed hatch covers over the thermal mass chamber, meaning that cold air was infiltrating directly into his heat storage system and robbing it of stored energy. McCabe calculated the infiltration rate by timing how long it took for wood smoke to clear from the sealed cabin. With all windows and doors closed, smoke from a small test fire dissipated completely in 15 minutes, indicating that the entire cabin air volume was being replaced approximately 4 times per hour. Campbell's Highland Cottage specifications called for air exchange rates of no more than once per hour for effective heat retention. The floor system required complete reconstruction using tongue and groove techniques that McCabe had observed during his railroad bridge work, but never applied to residential construction. He purchased 1,200 board feet of kiln-dried pine planking from the Territorial Mill in Douglas, specifying boards exactly 1 1/4 inches thick with precisely cut tongue and groove edges. The investment cost $48, nearly double the expense of standard rough-cut flooring, but the tight joints would eliminate the largest source of air infiltration. Installing tongue and groove flooring over the thermal mass chamber demanded structural modifications to support the additional weight and provide proper clearance for heat transfer. McCabe constructed a framework of hemlock joists measuring 6 inches by 8 inches, spaced exactly 16 inches on center above the stone mass. Each joist was notched to rest securely on the cabin's log sill plates, while maintaining a 4-inch air gap above the highest stones in the thermal mass system. The tongue and groove installation required precision that frontier cabin construction typically ignored. Each board had to be cut to exact length, fitted tightly against its neighbor, and secured with square-cut iron nails driven at precise angles to avoid splitting the tongues. McCabe used a wooden mallet and a piece of scrap lumber to tap each board into perfect alignment before nailing, ensuring that no gaps remained between adjacent pieces. The most technically challenging aspect involved sealing the junction between the new floor and the existing log walls. McCabe developed a technique combining Campbell's Scottish methods with solutions he remembered from railroad depot construction. He routed a 1/4-inch groove along the bottom edge of each sill log using a draw knife and chisel, then filled this groove with oakum caulking before installing the flooring. The tongue and groove boards fit snugly into these caulked grooves, creating an airtight seal that eliminated the major infiltration path where floor met walls. Window and door sealing required different techniques adapted from German joiner methods that McCabe learned from Heinrich Weber, an immigrant craftsman working on territorial government buildings in Douglas. Weber demonstrated the use of wool felt strips and wooden weather stripping to seal moving parts of doors and windows. McCabe installed quarter-inch thick felt strips along all door jambs and window sashes, compressed tightly when closed to prevent air movement while still allowing normal operation. The foundation perimeter presented unique challenges that neither Scottish nor German traditions had addressed adequately for log construction on frontier stone foundations. McCabe adapted techniques he had observed in Pueblo settlements during his railroad work in Colorado Territory, where thick earth berms sealed the junction between walls and ground. He mixed clay soil with chopped straw and prairie grass to create a caulking compound, then applied this mixture in a continuous bead along the entire perimeter where log sills met the stone foundation. The hatch cover system over the thermal mass chamber required the most sophisticated air sealing approach, since any infiltration here would directly compromise the heat storage efficiency. McCabe constructed double-layer covers using 2-inch thick pine boards for the structural layer, topped with a layer of wool blankets salvaged from worn military surplus, and finished with a final layer of oiled canvas. The covers were sized to overlap the hatch opening by 3 inches on all sides, creating a weatherproof seal when weighted down with iron bars. Sealing techniques around the chimney penetration through the roof demanded understanding of thermal expansion that McCabe had learned during locomotive boiler maintenance. The brick chimney expanded and contracted with temperature changes, creating seasonal gaps that opened infiltration paths. McCabe installed flexible clay and fiber caulking around the chimney base that could accommodate movement without cracking, then covered this with a lead flashing system that directed water away while maintaining the air seal. The completed envelope improvements transformed the cabin's thermal performance in ways that McCabe could measure immediately. The candle flame test now showed minimal air movement except near the chimney and one window that still required attention. Smoke clearance time increased from 15 minutes to nearly 1 hour, indicating that air exchange had dropped to approximately 1 change per hour, matching Campbell's Highland Cottage specifications. More importantly, McCabe could feel the difference in comfort levels throughout the cabin. Cold spots near exterior walls diminished noticeably as infiltration decreased. Floor surfaces that had previously felt cold even near the stove now remained comfortable to walk on barefoot. Most significantly, the temperature differential between areas near the thermal mass chamber and the far corners of the cabin narrowed from 20 degrees to less than 8 degrees. The envelope sealing work had consumed 6 weeks of intensive labor and cost over $70 in materials. But McCabe understood that without these improvements, his carefully constructed thermal mass system would have been essentially useless. Heat storage only functioned when heat retention was adequate to allow stored energy to warm living spaces, rather than leaking immediately into the surrounding environment. The envelope represented the crucial link between thermal mass storage capacity and actual heating performance that would determine whether his integrated system could maintain cabin comfort during the severe weather that Wyoming winters demanded. With his thermal mass chamber complete and envelope sealed, McCabe faced the critical challenge of developing an efficient charging sequence that would maximize heat storage while minimizing fuel consumption. His initial attempts in late April followed conventional stove firing patterns, building fires in the chamber's clay hearth for 3 hours each evening over 5 consecutive nights. The results disappointed him completely. Surface stones reached only 140 degrees Fahrenheit, barely warm to the touch, while stones deeper in the mass remained at ambient temperature. McCabe realized that intermittent firing allowed too much heat loss between burn sessions. The clay hearth and surrounding stones cooled significantly overnight, requiring each new fire to reheat the same thermal mass repeatedly, rather than building cumulative temperature throughout the system. Railroad roundhouse heating had taught him that thermal systems required sustained energy input to overcome heat losses and achieve working temperatures. But he needed to understand how this principle applied to his underground stone storage. The breakthrough came when McCabe encountered Paavo Niskanen, a Finnish immigrant lumber camp veteran who was passing through Douglas on his way to Oregon timber operations. Niskanen had grown up using traditional Finnish sauna stoves that heated massive stone piles to extreme temperatures through day-long firing sessions. He explained that effective stone heating required continuous combustion for 12 to 16 hours, maintaining steady heat input until the entire stone mass reached uniform temperature throughout its depth. Niskanen's technique involved building a foundation fire using small kindling and gradually adding larger fuel pieces to sustain combustion without temperature fluctuations. The key was maintaining consistent flame contact with the stone surfaces while preventing the rapid temperature swings that cause thermal stress and stone cracking. Niskanen demonstrated how to stack fuel so that new pieces ignited smoothly from existing flames, creating continuous heat output without the gaps that allowed cooling between fuel additions. McCabe adapted these principles to his chamber system through systematic experimentation during May. He began his first extended charging session at dawn on a windless morning, building his foundation fire with split cedar kindling arranged in a crosshatch pattern within the clay hearth. As the kindling established a solid bed of coals, he added progressively larger pieces, finger-thick pine splits, then wrist-thick cottonwood, finally arm-thick sections of seasoned oak that would burn slowly and maintain steady heat output. The challenge of sustaining combustion for extended periods required careful attention to combustion air management. McCabe discovered that his chamber's vent flap system could be adjusted to control airflow and maintain optimal burning conditions. With both flaps fully open, the fire burned too rapidly and consumed fuel wastefully while creating temperature spikes that risked cracking stones. With flaps nearly closed, insufficient air caused incomplete combustion and reduced heat output. McCabe found that positioning the flaps approximately one-third open provided steady airflow that sustained clean burning, while preventing excessive fuel consumption. Temperature monitoring throughout the charging process revealed thermal stratification patterns that McCabe had not anticipated. Using iron probes inserted between stones at various depths, he discovered that surface stones near the hearth reached 200 degrees Fahrenheit within 4 hours, while stones 18 inches away remained below 100 degrees. More problematically, stones at the bottom of the mass heated more slowly than those near the top, creating uneven charging that reduced overall storage capacity. McCabe solved the stratification problem by modifying his firing technique to create convection currents within the stone mass. Rather than maintaining a single concentrated fire, he learned to build multiple smaller fires in different areas of the hearth, rotating the burn locations every 2 hours to ensure even heat distribution. This technique required careful fuel management and constant attention, but it resulted in much more uniform temperatures throughout the thermal mass. After 16 hours of continuous firing, McCabe measured stone temperatures ranging from 260 degrees to 290 degrees Fahrenheit at various probe locations, indicating successful charging of the entire mass. The fuel consumption for this charging session totaled exactly 3 cords of mixed hardwood, significantly more than a typical week of conventional stove heating, but intended to provide heat storage for an extended period without additional burning. The discharge phase testing began immediately after McCabe sealed the chamber by closing both vent flaps and covering the hearth with clay tiles to prevent heat loss through the fire opening. He monitored cabin temperatures hourly using a mercury thermometer positioned 6 feet from the chamber location. Initial results exceeded his expectations dramatically. With outdoor temperatures holding steady at 35 degrees Fahrenheit, his cabin interior maintained 68 degrees for the first 24 hours after charging, with floor surface temperatures measured at a comfortable 59 degrees. By the 3rd day after charging, cabin temperatures had dropped only to 62 degrees Fahrenheit, while floor surfaces remained at 54 degrees. McCabe calculated that his sealed envelope was retaining stored heat far more effectively than conventional heating systems that lost most of their energy through continuous air infiltration and inadequate thermal mass. More importantly, he was achieving this performance without burning any fuel after the initial charging session. The most remarkable discovery came during the 2nd week of testing. Even 7 days after the charging session, with outdoor temperatures dropping to 28 degrees during a late spring cold snap, McCabe's cabin interior never fell below 56 degrees Fahrenheit. The thermal mass continued releasing stored heat at a rate that balanced ongoing losses through the envelope, maintaining livable conditions without any supplemental heating. McCabe refined his charging technique through multiple test cycles, learning to optimize fuel types and burning schedules for maximum efficiency. Dense hardwoods like oak and hickory stored more heat energy per cord than softer woods, but required longer charging periods to reach peak temperatures. He discovered that starting the charging process during warm, sunny days allowed solar heat gain to assist the firing process, reducing total fuel requirements by approximately half a cord per charging cycle. The integrated system of thermal mass storage, envelope sealing, and strategic firing had transformed McCabe's heating costs and comfort levels completely. A single 3-day charging session using 3.5 cords of fuel provided adequate cabin heating for 2 full weeks, compared to the conventional approach of burning half a cord every 3 days to maintain barely acceptable temperatures. The fuel savings approached 60% while delivering superior comfort and eliminating the daily labor of maintaining nightly fires. The ultimate test of McCabe's integrated heating system arrived without warning on February 18, 1873, when a massive Arctic air mass descended from the Northern Territories and trapped the Wyoming region under the most severe cold snap in territorial memory. Weather observations at Fort Laramie recorded temperatures dropping to minus 31 degrees Fahrenheit on the first night, with sustained winds exceeding 20 miles per hour, creating deadly wind chill conditions across the high plains. McCabe had completed his final charging session just 4 days earlier, bringing his thermal mass to peak storage temperatures before the weather system arrived. His timing proved crucial because the extreme conditions made outdoor work impossible and wood gathering potentially fatal. Neighbors who relied on daily fuel collection found themselves trapped in their cabins with dwindling wood supplies as snow drifts blocked access to their wood piles, and wind made fire starting nearly impossible. The Brennan homestead, located 2 miles south, epitomized the crisis facing conventional heating systems during extended extreme weather. Thomas Brennan had stockpiled only enough split wood for normal winter consumption, approximately 12 cords stored in an open shed 50 yards from his cabin. By the second night of the freeze, drifting snow had blocked access to the woodshed completely, forcing Brennan to burn furniture and interior wall planking to maintain minimal heat. His cabin interior dropped to 28 degrees Fahrenheit on the third night, despite burning continuously, and ice formed on interior walls near windows and doors. Marcus Stern's cabin experienced even more catastrophic failures when his chimney system succumbed to thermal shock during the fourth night of extreme cold. Rapid temperature changes between the overheated chimney interior and the bitter outside air cracked the mortar joints, allowing cold air to pour down the flue directly into his living space. Stern attempted emergency repairs using mud and rags, but the compromised chimney created dangerous backdrafts that filled his cabin with smoke while providing minimal heat. He was forced to abandon his claim temporarily and seek shelter at the territorial offices in Douglas. McCabe's system performed flawlessly throughout the 9-day ordeal without requiring any emergency intervention or supplemental heating. His cabin interior temperature never dropped below 61 degrees Fahrenheit, measured at 6-hour intervals using his mercury thermometer positioned away from direct thermal mass influence. Floor surface temperatures remained between 57 and 60 degrees throughout the crisis, providing comfortable conditions for all normal activities, including sleeping, cooking, and indoor work. The thermal regulation during the extreme event revealed sophisticated heat transfer principles that McCabe had not fully understood during his earlier testing. As outdoor temperatures plummeted, the temperature differential between his stored heat and the cabin interior increased the rate of heat transfer from the thermal mass. This self-regulating effect meant that the system automatically provided more heat during the coldest periods while conserving stored energy during milder conditions. The massive stone storage acted as a thermal buffer that absorbed temperature fluctuations and delivered steady, predictable heat output regardless of external weather variations. McCabe documented the system's fuel efficiency during the crisis, with precise measurements that demonstrated the economic advantages of thermal mass heating. His pre-storm charging had consumed 3.5 cords of seasoned hardwood. During the 9-day freeze, he used only one additional half cord for a single supplemental heating session on the 7th night, when outdoor temperatures reached minus 29 degrees. Total fuel consumption of 4 cords provided complete heating for 11 days, including the charging period. In contrast, neighboring homesteads that survived the freeze consumed dramatically more fuel while achieving inferior results. The territorial supply agent Benjamin Carson conducted informal surveys after the crisis, and documented that conventional stove-heated cabins averaged 1.5 cords of fuel consumption every 3 days during the extreme period. Those homesteads that maintained barely adequate interior temperatures above 40 degrees Fahrenheit consumed approximately 9 cords total during the same 11-day period, more than double McCabe's consumption while delivering far less comfort. The social dynamics surrounding McCabe's heating success shifted dramatically once neighbors observed the performance differences. James Hawkins, the Territorial Land Office foreman who had previously dismissed the thermal mass concept as unnecessary complexity, visited McCabe's cabin during the 6th day of the freeze. Hawkins found McCabe working comfortably in his shirt sleeves while outdoor temperatures registered -26 degrees, and immediately requested detailed explanations of the construction techniques and operational procedures. Sarah Brennan, whose husband had barely survived the freeze using emergency heating measures, became the first neighbor to request assistance implementing thermal mass storage in her own cabin. McCabe agreed to provide technical consultation during the spring construction season, sharing Campbell's Scottish cottage techniques and his own refinements developed through systematic testing. Sarah's request initiated a pattern of knowledge transfer that would spread McCabe's innovations throughout the regional homesteading community over the following years. The most significant validation came from unexpected quarters when railroad construction supervisors working on the Union Pacific Western Extension learned about McCabe's heating success through territorial supply networks. Railroad companies were struggling with heating costs in construction camps and maintenance facilities where conventional stove heating proved inadequate and expensive. Company engineers visited McCabe's homestead during spring thaw to evaluate the thermal mass principles for adaptation to larger-scale commercial heating applications. By 1875, 3 additional homesteads in the immediate area had constructed thermal mass heating systems based on McCabe's design principles. Benjamin Carson began stocking riverstone, fireclay, and tongue and groove flooring materials to support the growing demand for thermal mass construction components. Carson's business records showed that homesteaders using thermal mass systems purchased approximately 40% less fuel annually compared to conventional stove users, while reporting significantly higher satisfaction with heating comfort and reliability. The technical documentation that McCabe maintained throughout his system development attracted attention from territorial engineers and eventually reached federal building authorities responsible for constructing government facilities in Western territories. Military post commanders facing enormous heating costs in frontier installations requested copies of McCabe's construction drawings and operational procedures. The systematic approach McCabe had developed for thermal mass sizing, envelope sealing, and charging schedules provided a replicable template that others could adapt to their specific climate conditions and building requirements. McCabe's innovations represented more than individual ingenuity solving a personal problem. His integration of Scottish cottage traditions, indigenous heat storage methods, and railroad engineering principles demonstrated how combining diverse knowledge sources could produce solutions superior to conventional wisdom. The extreme weather test had proven that traditional approaches to thermal comfort, properly applied and systematically refined, could outperform accepted modern methods while reducing costs and improving reliability. The quiet revolution in frontier heating had begun with one man's refusal to accept that freezing through Wyoming winters was simply the inevitable price of homestead independence.